Okay, we're going to start writing Taylor polynomials to approximate functions that are not polynomials, such as f of x, using using this formula here. Hopefully, you've opened up the two PDFs. If not, go ahead and pause and do so. They have this formula here, which is the formula for Taylor series polynomials. You may not be able to see it here, but it will be on the PDF pretty clear. Basically, there's some components to it. The first term is simply the value of the function at a being the center. So in this case, for my first example, and all my examples today will be centered around 0. So it'd be f of 0, so you just plug in 0. The next term is you need the derivative, okay, times the first order polynomial. Again, so it's derivative with the a in it, the center is 0. And then here it's x subtract 0, okay, because center is 0 and that's a. And then we need the second derivative divided by 2 factorial. All these coefficients are significant. The coefficients here, the derivative. Then we've got the double derivative with the 2 factorial underneath it. These are called the coefficients. They're in front of the variable part. So this would be the x squared part. The third coefficient is here, which is the third derivative at 0, 3 factorial. So when you do your assignment, the first assignment after the 3 videos, the first part's quick check part is basically finding those repeated derivatives, which is obviously a skill we need here. Sorry, have to pause. Ha ha ha. Okay. Now, so there's kind of some phases in order to do this. We're going to get these derivatives and find them at their center at 0. So the first thing I'm going to do is I'm going to list out my orders. The 0 order, that means 0 derivative. Then I'm going to do 1, 2, third derivative, fourth derivative, and so forth. I may not do all of them, but I certainly want to do the nth derivative. The function is e to the x. So 0 derivative is just e to the x. The first derivative of e to the x is e to the x. Obviously, this gets more complicated because the derivatives are hard. The second derivative of e to the x is e to the x. Repeat that, derivative of e to the x, e to the x. So you have your repeated derivative. Now, the coefficient requires me to put the a in for those derivatives. So I'm going to plug in 0. So second kind of phase is to plug in 0. So e to the 0, 1, e to the 1, e to the 2, e to the 3, e to the 4. I am so sorry. E to the, each time I'm plugging in 0. So it's 1, 1, 1, 1. So I have now ones. I apologize. Each time I'm plugging in 0 and they're all the same. So I got confused. It was so easy. The next step is you need to divide each one of these by the factorial. This one doesn't have a factorial. This one is a 1 factorial. Technically, this one's 0 to the 0 factorial, but 0 factorial is defined to be 1. And then 1 factorial is 1, 2 factorial, 3 factorial, and so on. So the 0 term divided by 1 is 1. And these are this is my coefficients stage. Creating the coefficient. This is the derivative stage. So there's kind of stages. Find your derivative, find the coefficient. So 1 divided by 1, or 1. Then I've got 1 divided by 2 factorial, which is 1/2. Then I've got 1, because I plugged in 0, which gave me the 1. 1 divided by 3 factorial, which is 1/6. And then 1 divided by 4 factorial. I'm going to leave it as 1 over 4 factorial. Typically we do that. I should have kind of left that as 3 factorial, but it was so simple. So the factorial, the coefficient, is always 1 over, And each time these are my n's, that's 1 over n factorial. That's my coefficient, and its general term. Now, the final step is to go ahead and write the Taylor series polynomial. So, the function f of x is equal to, if I write the whole series out, is equal to f of a, which is 1. Then I'm going to do the derivative at a, which is 1. The coefficient's 1. So plus 1 times x minus my center, which is 0. Plus, now the second derivative divided by 2 factorial, which is my coefficient of 1/6, times x minus center square, plus my coefficient 1/4 factorial, x minus 0 to the I skipped one, I apologize. 1 over 3 factorial, 3, plus 1 over 4 factorial, x minus 0 to the 4th, plus dot, dot, dot. Now, obviously you want to simplify this. I didn't need to write all that out. The function is equal to 1 plus x plus 1 over 2, which is 1 over 2 factorial, x squared, plus 1 over 3 factorial, x cubed, plus 1 over 4 factorial, x to the 4th, plus dot, 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 which equals. Now we can write that as a summation. Summation. Now my first one was 0. So my n equals 0 to infinity. Now the pattern works this way. I have a 0 here, and I have the 1. 1 is x to the 1. 2 gives me this one. 3, and so on. So every single time, if I map this out, this is the 3. See how these are both 3s? See how this is 2? These are 2s. This one's pretty straightforward, and it's easy to write the nth term. And the nth term, each time, is 1 over n factorial x to the n. Okay, now this is equal. Now, when I truncate part of the function, in other words, I use it to approximate, I cover this up. If I want a second order, that's my second order polynomial. It's not equal anymore. It's now going to be approximately equal because I've truncated part of it. Now I could do the third order. If I go this far, now it's a third order Taylor polynomial approximation equation, and it's approximately and so forth. So to put that together, pause. I'm going to write out the third ordered polynomial, Taylor polynomial. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, and I'm done because I'm to the third. Okay, this, if I plug in 1, will be equivalent to e. So let's try that real quick. So let's plug in 1 real quick, and that's going to give me 1 plus 1 plus 1 2 factorial times 1 squared plus 1 over 3 factorial 1 cubed. If I do that, I get this approximation is equal to 2.6667. Okay, that is a third order approximation for this, for f1. I plugged in 1 to my polynomial, F1. And F1 happens to be equal to that, which is approximately 2.72. See how close my value is? Now, just briefly, even though error may not be on the assessment, the error is your mistake. So it's the absolute value of e to the 1 minus the polynomial. If I do a third order error, it's that, which is basically e subtract the 2.6667, which gives me my approximation of an error of 0.0516. And you can confirm those numbers if you like. Now, Lagrange is my favorite. Lagrange for the third order polynomial. Here's the third order polynomial. So I've gone this far. If I look at this, I've truncated right here. The Lagrange is the very next term. So my Lagrange error, which should be approximately the same as this error, is equal to 1/4 factorial x to the 4th. Well, our x here, we were trying it at 1, which gives me an approximation of my error of 0.0417. So the actual error is this. However, sometimes we can't actually find the function value, so we're going to have to use Lagrange to approximate our error in our problems. Keep in mind, I'm doing these for center of 0. Now I'm going to play with your mind a little bit, and then I'm going to show you an easy way to deal with these. Little pause. Okay. E to the, now I'm going to write this function, which is not a polynomial. There's part of it that's a polynomial. Notice there is part that is, but I'll come up with that later. But right now, I'm going to write the Taylor polynomial centered at 0. So I'm going to follow the same steps. First thing is, I'm going to write my degrees. 0, 1, 2, 3, 4. I don't know if I'm going to get that far with this. Let's try this. Now, we're going to take the first one. We don't have to take any derivative. It's just e to the x squared. So we're going to create those coefficients. Right now, we're on the stage of the derivative part. We're on the dir part. Now I'm going to take the first derivative. E to the u times u tick. Now I'm going to take the derivative again. Notice it's the product rule, and this makes this difficult, so I'm going to cheat. I'm going to go through and do all this product rule and make it in factored form, and I'm going to get 2 plus 4 x squared e to the x squared. I did it already for you. So that's my second one. I'm going to get these all messed up now. Let's move this 3 over here. 3. Now my third would be, I'm going to do the derivative. Now again, this is a product, and I have to do the product rule and all this good stuff, and then get common factors. You wind up with 12x plus 8x squared, x cubed. I think that's cubed. All or times e to the x squared. Now I'm obviously skipping over parts of this because it's not that important. The fourth, and I'll show you later, 4 is, I'm going to do this again, and I'm going to wind up with 12 plus 48x squared plus 16x cubed, all times e to the x squared. And then we got to keep doing that. Pretty insane, you must admit. Okay, now I'm going to plug in the center. The center here is x is 0. So to finish this off, I'm going to plug these in. I'm going to do them. I'm going to cheat a little bit. This first one's pretty easy. E to the 0 squared is 1. Then I'm going to plug in 0. This one's pretty easy too, because 0 times all that is just 0. But the next one's become more complicated. Maybe not. If you plug in 0 here, you get 2. What was hard is actually getting those derivatives. It takes forever. Then the next one I plug in, I get 0. That's why I was not too worried about my screwed up power there. The next one, the 4, I get 12. And then so forth. Okay, so far I've done the derivative part, and I've got my derivative values at the center of 0. Now the next step, next phase, is you need the coefficient stage. So now let's create the coefficients. The coefficients is divide this by 0 factorial, divide this by 1 factorial, divide this by 2 factorial, divide this by 3 factorial, divide this by 4 factorial. So my coefficients, 0 factorial is defined to be 1. You can confirm that in your calculator if you like. 1 plus 0. Sorry, not plus. Just create my coefficients. 1, 0, 1, 0. And 12 divided by 4 factorial simplifies to 1/2. All right? Now, once you have the derivative stage and you've got it at the center, which is at 0, you create your coefficient by dividing by the factorials. Now you can create the polynomial. So f of x is equal to ex squared, which is equal to, now I'm going to have to consider the infinite series if I'm going to call it equal, 1 with no x plus 0 to the x subtract a, which is my center, 0, plus 1 x subtract 0 square plus 0 x subtract 0 to the third plus 1/2 x subtract 0 to the fourth plus dot dot dot. I can write out this, but I need to straighten it out. Obviously, you can see that I've got these fat zeros in here that I don't really want to have in here. So let's get rid of those. So this equals 1 plus x squared plus 1/2 x to the fourth plus dot dot dot. Now, we kind of need to write that nth term, and the way to do that is you're going to come up here. I'll actually write them down here. This was my 0. This was my 2. This was my 4th term. Okay, my 4th order part. Okay, so if I'm going to write my nth term, I have to create the pattern here. Now, it's not easy to see the pattern using the 1, so I'm thinking 2, and that's 2, that's 4, that's 4. So I think that the x is to the n power. But notice how it skips. So first term, second term, third term. So I want to make it 2 to the n. So if I plug in my first, my second is 2. 2 to the n is the second term, 2 to the n. So I'm going to start with 0, and I'm going to go to infinity, but I got to go by 1s. These are going by 2s. So that's why I get this. Over, and I'm going to put this coefficient down here. Now, this one was a 1, so you can think of 1 over 1. It's 1 down at the bottom. The top is clearly 1, so I can put a 1 there, but the bottom is what keeps changing. The next one, well, that's a 4, that's half of that. That's a 1, that's half of that. So I'm going to take n divided by 2. Factorial goes on the bottom. Now it's a little messy. A little bit of practice and that quick check will help with that component. Now, the biggest thing I want to show you, and here's the tip off, is when you look at this original function I had here, this looks like the function e to the u. E to the u, we did that one already, and we found centered at 0, we got this polynomial here. We got this Taylor polynomial like this, all right? Now, we went through all this, and I want to emphasize the nastiness of all this garbage. I mean, I really don't want to have to do this each time because those are really difficult. What I want you to observe when you're looking at the function you're trying to get the polynomial for is I want you to look for parts that are polynomialed. That's a polynomial part. So what that means to me is I can not worry about that part. I can consider this. I'm going to think of taking the Taylor series polynomial of this. If I do that, consider this. I get this function. Now this is my function. The only thing different between these two terms is a polynomial. And I'm creating a polynomial. Which essentially means all I have to do is plug in x squared wherever I have an x squared. This function had an x in it. That's a simple version. Since this is given to be a polynomial, all I have to do is plug it in for x every time. So if I do that, the easy way to do this problem is not to do the repeated derivative of something very complicated. It's to look at the function and ignore the polynomial part, focus on the non-polynomial part, take its Taylor series polynomial, create that, and then all I have to do is substitute in the x squared wherever an x. So the actual way I would have done it is wrote this one out. I would have created this polynomial, which I can do. Or you can memorize the Maclaurin series polynomials, which are on page, see if I've got that written down for you. That is on page 491, I believe. All right, it'll come up on one of the notes. So to finish this off, what I would have done is wrote this out, then I would wrote 1 plus, get rid of the x, replace it with x squared. Get rid of the x squared, or the x, and put x squared in its place. That gives me x squared squared, which is x to the 4th over 4. Plus, plug in to x squared, gives me x to the 6th over, sorry, why did I write 4 there? 2 factorial, 3 factorial, plus plug in x squared, gives me x to the 8th over 4 factorial, plus dot dot, and made it really easy for me to write a lot of terms. And now this was the series written out. All I have to do now is consider that I'm plugging in the x squared up here. Okay, so and it should work just handy dandy, which gives me, I'm losing it, where's it at? It comes out to be the same thing as this one up here. I don't know why I'm having such a hard time with that one. Okay, the only thing hiccup is you got to be careful with the factorial part at the bottom. So you plug it in, you get x squared to the n over, and now you're skipping terms, so you want to do the n divided by 2 factorial. This is a simpler form, so let's get down to it. Let's look at this next one and skip over to make it doing this the difficult way. What I'm going to do is I'm going to look at this term. I see this, and so the very first thing is I'm going to write out that e to the x polynomial. And again, it's called a Maclaurin, and it makes life real easy. So if I consider e to the x, it's equal to 1 plus x squared over 2 factorial plus x to the 3rd over 4 factorial over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. Now, instead of going through all that process of taking the derivative of that repeatedly, all I have to do is go e to the 3x then would be 1 plus, plug in 3x, gives me 3x squared over 2 factorial plus 3x to the 3rd over 3 factorial plus 3x to the 4th over 4 factorial plus dot dot dot. This nth term here was x to the n over n factorial. So this one becomes 3x to the n over n factorial. And all I have to do is slap the summation around it and I'm good to go. Example number 4. Again, these are all centered around 0, and this works when they're all centered around 0. Notice this is the non-polynomial part. This is the polynomial part. I don't have to create a Taylor polynomial for a polynomial. It is the polynomial. So this part remains. So we have x squared. It's already a polynomial. And we're going to multiply that times the polynomial for this, which was 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial plus ... Now that means that instead of doing the product rule and doing the multiple derivatives that required this, and it's very difficult, all I have to do is consider this is the polynomial part times the non-polynomial part, write the Taylor polynomial for it, and distribute that x squared. Oh, I'm distributing. It's a 3, sorry. X to the 4 over 2 factorial plus 2 times x squared times x to the third is x to the 5th over 3 factorial plus x squared times x to the 4th is x to the 6th over 4 factorial plus ... Now let's look at the pattern. This equals the summation of n equals 0 to infinity. So let's look at this carefully. This is my 0 term. 1, 2, 3, 4. So if I look at writing this out, the factorial parts are straightforward and the same every time. It's always the same as my n over. Now these guys, 0, that's a 3, that's 2 goes to 4, the 3 goes to a 5, the 4 goes to 6. So it's got to be x, but I have to add 2 to my exponent. So there you go. Again, real nice. Look at this one. Example 5. Once again, this component here, this is already the polynomial. That's the part that's not. So that means I'm going to need the Taylor polynomial for this one. So my function equals, hopefully you can see that, is e to the x, which was 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial plus ... minus 1 minus x minus 1/2 x squared. Which, if you look at that, that's going to take the 1, take away 1, x take away x, and then x squared over 2 factorial is just over 2, and those cancel, leaving me with a reduced polynomial of x to the 3rd over 3 factorial plus x to the 4 over 4 factorial plus ... Now, if I choose to write this as a series, I can just go ahead and say, I'm going to start with 3's. So I could write this as n equals 3 to infinity and just go n factorial over x to the n. That works. Typically we write these with starting at 0. So if I do that, that means that's a 0, now that's a 3. That's a 1, that's a 4, which means basically I'm adding 3 each time. So it's n plus 3 factorial at the bottom, then x plus n plus 3 as my exponent. All right, quickly look at these two examples, because these two are garbage. Okay, this first one, I want you to note that both of these, I can write the Taylor series polynomial of this centered around 0, and I can write these. But if I try to do that, I got an infinite number of polynomial terms here, an infinite number of polynomials terms here. So basically, this one would be a nightmare because we'd have to do each step. We'd have to take the derivatives, plug in the center of 0, in this case it's center of 0, and then I'd have to find the coefficient and then write the polynomial. Not a fun one. Probably not one you're going to be tested on. Now I hope they give you this one. Example 7. This one, oh my gosh, why would I write, okay, so if I want the Taylor series polynomial for the f of x, I'll do it for you. Here you go. I put this on a test one time and people did the whole Taylor series process and wound up with that answer and got really mad. I'm going to save you the hassle. Look, that's a polynomial. Why would I be writing a Taylor polynomial when that is a polynomial? You follow me? So Taylor polynomial parts don't get done. We don't do those. We don't need to. They're already polynomials. Okay. To practice in here, I knew I had this written somewhere. At the very bottom of the page here, and hopefully you can see it, and you can. To practice these, stop right now and just take a few minutes, and it may take you a little bit, like 2 or 3 minutes per, but I want you to try to write the Taylor series polynomial of cosine x, ln 1 plus x, and 1 over 1 plus x. All three of those centered around 0. If you do that, you can check those. Those are special kind of Taylor series polynomials called Maclaurin. And all of those Maclaurins are written out on page 491. Some people are inclined to memorize those because if you know those, just like I did with the e to the x one from at the very beginning, this one here, where I had e to the x, all I do is if I know the Maclaurin is all I have to do is plug in the polynomial part and I'm done. So some people actually memorize those pages and it was much easier and time consuming. Considering only a 45-minute exam, that might be helpful. All right, that's that one. Your next video, I would take a deep breath. Your next video will be on centered not 0. Anything centered not 0.